All right, so in this video, we're going to take another look at some examples dealing with power series and how to determine where they would converge. So in this example, much like the last, I'm going to go ahead and start off with a ratio test, in which case I'm going to have the limit as n goes to positive infinity. And if you remember, the absolute value bars would do away with this guy, but we are still going to need them in our work down here because of this x. So I'm going to have now the x raised to the 2n plus 3. Again, that's me evaluating the n at n plus 1, distributing and cleaning that up, divided by the 2n plus 3 factorial for the same reason. Plug in the n plus 1, distribute the 2, and combine. Divided by the original, which is going to be me multiplying by the reciprocal. So I'm going to have this 2n plus 1 factorial over x to the 2n plus 1. And finish up by closing that absolute value bar down. All right, so I'm going to go ahead and clean this up a little bit. The algebra here is not anything different than you've seen in the past, but I do just want to make it clear. So I've got x to the 2n times x to the third. In the denominator now, I'm going to have 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And then the 2n plus 1 factorial on top, and the x to the 2n times x to the first on bottom. Now, let's see what cleans up here. Well, the x to the 2n's go away, the 2n plus 1 factorials go away, and in fact, this guy here would do away with that, leaving us with an x squared. All right, so I'm going to go ahead now, much like the last one, I'm going to pull the x squared out. And you can certainly keep the absolute value bars on it if you really want to. Otherwise, noting that x squared would always be positive. If you just wrote the x squared, you would not be wrong. So I'll go ahead and finish that up. And then we have this 2n plus 3 and a 2n plus 2 that we're taking the limit of as n goes to infinity. Well, when you take this limit, this guy right here goes off to 0, which means that we're going to have now an x squared times 0, which is less than 1 for all x. So for any value we plug in for x, this is always going to be less than 1. It's not even going to be equal to 1. It's always going to be less than 1 for every single x value you plug in, which means that in this case, we have an interval of convergence from negative infinity to positive infinity. Every single number you plug in will work. And the radius of convergence, if you remember from that theorem, this would be r equals infinity. So there's our interval of convergence and radius of convergence for this particular power series. All right, so in this example, once again, we've got a power series. We're determining convergence. We're determining where it converges to, or what would force it into convergence. And so I'm going to move forward a little differently. I mentioned before that the ratio test is generally a good starting spot. And you could certainly use the ratio test on this problem. However, I wanted to pick one where we could also move forward using the root test. If you remember, the conditions of the root test are similar in drawing the conclusions, but the setup is a little different. So here we'll have the limit as n goes to positive infinity, and then we'll go ahead and have this absolute n to the n, x to the n, and that's all going to be raised to the 1 over n power. And it's pretty clear why I chose the root test in this particular case. That's going to give us a very simple n times the absolute value of x. So if you wanted to pull out the absolute value of x, you certainly could. But given the fact that we just have this remaining n, it might be intuitive to see it either way. You can see that this guy here is pretty clear, goes off to infinity. So now we have to think about what's going on here. We've got this absolute x times infinity. Well, if x is 0, we know that it's going to converge, right? If x is 0 from start, you can see that it's going to converge. If x is not 0, then we have some positive number because of the absolute value bars times infinity, in which case, would go to positive infinity. And since positive infinity is bigger than 1 for all x, we know that the only possible option is for this thing to converge at x equals 0. So the interval of convergence would be the x equals 0, and the radius of convergence would be r equals 0. So again, the conclusions of the ratio test and the root test are the same about comparing this to 1. The fact that this thing is always going to be positive infinity for all x tells us the only case that we have is for x to be 0. That would, of course, zero this thing out. So our interval of convergence and our radius of convergence now for this particular case.